at mirrorBits. Let's take a look. Reverse the order of the bits in a given integer. That's a very clear instruction. Wow, I think this might hold the record for the shortest description yet. Wow, very succinct, very concise. There isn't any kind of story that they've wrapped it in or anything like that. And you know, I respect that. Okay, so basically they do give us a quick example over here. So we've got 97, and they're saying that the result here would be 67. It might be kind of tough to grasp that. I mean, just by looking at it, like, wow, 97 being a 67 when we mirror the bits. And they make it more clear here by showing us, well, 97 is 1100001. And so if we flip those, we get 10000011, which is 67. Okay, so cool. That's basically what we want to do. I get it. So let's take a look at it in, again, sort of the most literal possible way. We'll be starting with, by doing our toString with an argument of 2. So in fact, let's do that right off the bat. So we'll say let bin be assigned the value of a dot toString 2. I'm using bin just as a shorthand for binary, because this is our binary representation of this thing. And then what do we want to do with it? Well, I'm going to put it into an array, so I'll use this strategy for putting it into the array. Again, other strategies are totally fine here. It's up to you if you prefer a dot split or an array.from. Hey, you do you. But for now, we're going to use the spread operator and the array literal. It's my fave. Okay, so we've got our array here, and now we just want to reverse it. Array.reverse. Whoops. Okay, there we go. Array.reverse. Now, I think we found in one of the previous challenges that array.reverse is a mutating method. So I don't have to say array is assigned the value of array.reverse, even though that would work. So it's one of these methods that, yes, it will modify the array, but then it will also return the result of that modified array. So it's, it's redundant, but it's neat. Okay, so what do we want to do with this? Well, it's reversed now, so now we just need to pick up the pieces, get it back to what we want it to be. So now we'll say, let flipped be assigned the value of array.join. Okay, so .join is the opposite of .split. It's basically going to take all of the, in fact, you know what? Here, let's do a console log of our array here just to see what it looks like. In fact, you know what? Let's do a console log before and after. We'll see the before and after pics. It's like a regular infomercial here. So, okay, cool. And then, in fact, you know what? Let's just return flipped. That'll be fun. Just to sort of, explore how this .join is working. Right, so this is the original, this is the reversed, and then basically for .join, we're putting these all together, we're pasting them together. And what are we using as the adhesive? Well, just an empty string. But it doesn't have to be an empty string. It could be a string with some stuff in it, but that's not really what we want here. I just wanted to sort of show how .join is working, why we have this empty string in here. I'm not sure if we actually need it, if we gave it a non-argument, if it would actually work or not. I guess we'll find out in just a sec, hopefully. But yeah, okay, so we do need it, I guess, because otherwise by default it's going to put in a comma. So we're going to give it an empty string to say, hey, I don't want the comma. Okay, good. All right, and then we don't want to return flipped. We want to return the numerical value of this. So we want to parseInt of flipped. Whoops. ParseInt because we want it to be an integer. So we'll take a look at what this is going to return, and that's not right. Oh, this one was. Okay, lucky. But anyway, this one is saying, no, that's not working. And why is that? Well, it's because we did the parseInt as though this was the actual number, like the decimal number, like as though we are actually looking at the number 1,000,011. Well, that's not what we want. We don't want the number 1,000,011 because this is not decimal. It's binary. So we give it a second argument. It's an optional second argument. You can give a parseInt. That explains what the base is. Okay, cool. So this is working. Looks good. It's looking like it's passing the tests. Again, I am going to sort of put this all together, just sort of, for fun. I don't think it's going to increase the clarity. In fact, it may accomplish just the opposite of that, but, whoops, mouse froze for a sec there. That's no good. Array.reverse.join. So, okay, I guess I'll just, whoops, I don't want the semicolon in there, but I'll just replace array with array.reverse, because like we saw before, it should work whether we're returning that one or whether we're just using it to mutate the existing array. Array was this thing after all, so we'll replace array with that thing. And finally, since bin was just a.toString with an argument of 2, let's just put that in there. We'll clean this up a bit, we'll run it, and what we find is it passes all the tests. Okay, so cool. Well, actually, I shouldn't say all the tests, and we should see if it passes the hidden ones as well. Let's find out. What's the verdict? It wins. Okay, great. Nice job. Okay, so that's good. Hey, look, we're halfway through the corner of zeros and ones. That feels good. All right, we'll close that for now. Let's go back to the description. And yeah, okay, so this is working, but I kind of don't like it. You know, I'm not a big fan of this toString business. If we can avoid converting the number to a string, if we can just work with it as a number, then that's probably better, you know? When you love someone, you should accept them for who they are. You know, you shouldn't try to turn them into someone else. So I really want to show my love for this number a here. And I'm not going to try to turn it into something it's not. I'm not going to try to turn it into a string. I'm going to accept it for what it is, a number. So we'll treat it as a number. And basically what we want to do is we want to pick apart all the digits in the number, right? All the digits in the binary representation anyway. So we'll take a look at how to do that. But before we do, let's just review how we've done this in the past for regular decimal numbers, because this is something we've done before. We've had to pick apart the digits. So let's just say, for now, let's just do an array, and it's going to be called digits, okay? Just something simple like that. And I'm just going to say while a, okay? So it's something we've done before where we have a number, let's say it's 972, and basically the way we treat this is we want to say, okay, first up, we want to grab the 2 here, we want to take that number, and we want to store it, and then we want to get rid of it. So the way we're going to do that is we'll do a mod 10 to get this number, because if we were to divide this by 10, what would the remainder be? It would be 2. Okay, so we'll do a mod 10, and then we'll divide this out. So we'll divide by 10, and we'll take the floor of it, right? So then basically the mod 10 of this would be 2, and then when we divide this by 10 and take the floor, we get 97. Dividing by 10 would give us 97.2. Taking the floor would give us just the 97. Okay, so basically the idea is, well, we'll continue with that. We'll get a 7 from this, you know, mod 10, we get the 7. Divide by 10, we get 9.7. Take the floor, we get 9. Keep this going until it's a 0. So that's why I'm saying while a, instead of, you know, like while a is greater than 0 or something like that. It'd still work if we did it that way. But while a is a little more efficient, I guess. So we're going to say something like this. Digits.push, and what are we going to push in there? We're going to push a mod 10 for now, and then we're going to say a is going to be assigned the value of Math.floor, a divided by 10. Okay, and then let's return the digits from there. We'll see if it's picking those apart. Okay, there we go. So we get 7, we get 9, those are the digits. We get just 8 there. Well, that's the digit. I guess we might as well put as a custom test 972, and I don't know, let's just put a junk value in there. It doesn't need to be right. We just need to make sure if it's actually picking these apart the way we want to. And while that's calculating, big thanks to ATD285 for the donation. ATD says, I think you should rename yourself to number.positiveInfinity cool. Instead of 0 cool. I get it. Okay. Can't thank you enough for all the time you devoted to help me and others learn. You have a true talent for teaching. ATD, thanks a lot, man. You have a true talent as a viewer. So, is this working? Yeah, it is. Okay, so we sort of get, in a sense, 2 benefits here, because on one hand, it's taking all the digits out. On the other hand, it's actually doing the reversing here, which is nice, you know? It's reversing the digits. Maybe we could get it to do that in a different way too. Like, let's say let reversed be a number that's going to start at 0. And then what are we going to do with that? So instead of pushing instead of pushing a mod 10 to digits, we're going to put it into the reverse somehow. So we're going to say const digit is assigned the value of a mod 10. And then we're going to say reversed is going to be assigned the value of reversed times 10 plus digit. Okay, I think that should work. Let's find out. First of all, reversed. Okay, yeah, let's get that going and we'll see if it gives it. So 972, we should expect 279, I guess. Yeah, 279, there we go. So that's great, that's working. Okay, nice stuff. So basically the idea here is that every digit that it pulls off of A, it's putting it onto reversed here. So basically reversed starts as 0, and then we say, okay, multiply that by 10. Well, 0 times 10 is still just 0. Maybe I should write this out. So we start as 0. And in fact, here, let me clear that. Let's get two cool colors here. So maybe like a pink and an orange. Or hey, you know what? 'Tis the season, right? So here, we'll say reversed, and here, we'll put A over here, and then we'll put reversed over here. I guess I'll just use an R for reverse. Maybe I should have made it B, just to sort of complement the A, but anyway, who cares? All right, so A starts as 972 over here. R, reversed, is going to start as 0. Okay, and then what happens? So as we're running through this, the first digit is going to be 2. Okay, so we say reversed is going to be reverse times 10, well, just 0 times 10 is still 0, plus the digit, which was 2, so R is going to become 2. And then what are we going to do with A? Well, we're going to say it's going to be assigned the value of Math.floor of A divided by 10. Well, A divided by 10 would be 97.2. Floor that, we get 97. Okay, so look at that. The 2 basically made its way onto the other number. Cool. So let's continue that process. We run this again and we say, now our next digit is going to be this. It's going to be the 7. Maybe I should have had a separate column for what the digit is, but oh well. I have faith in your guys' memory and visualization skills. Okay, so basically the idea is the next digit is going to be 7. It's just the last digit over here. What are we going to do with that? Well, we're going to say reversed is reverse times 10. So it was 2 multiplied by 10. It'll be 20. And we add on digit, so it'll be 27. Because digit was 7. And then we say A, well, we're going to divide it by 10, take the floor. Divide by 10, we get 9.7. Take the floor, we get 9. Now look at this. Another digit has made its way onto R, and it looks like the order is what we want. So that's good. Okay, now, the next digit is going to be the last digit available. It's just going to be 9. A mod 10, in this case, is just A. It's just, because this is less than 10, so it's just, it is its own remainder when divided by 10. Okay, so basically the next digit is 9. We're going to multiply reversed by 10, so we get 270. We're going to add on the 9 to it. We get 279, and that's going to leave us with an A value of 0 when we divide it by 10 and take the floor, because we get 0.9 divided 0.9 is what we get by dividing by 10. Floor that, we get 0. So we say, while A, well, A is 0, so we're not going to repeat this any longer. We've got our number, it's reversed, it's 279, we're done. We reversed it. Okay, so any questions, comments, concerns on any of that stuff? Hopefully this is making good sense. If you have any questions, let me know. As for now, let's move on with this stuff. So we've got our reversed, and yeah, I think I am just going to change that to B just for the sake of simplicity. B. We'll see if that's going to run. Yeah, some of the core challenges are definitely a step up in difficulty, though I would say, ATD, that I find the way it progresses is a little more... I think it's a better learning curve than the intro. I find the intro really just throws in some curveballs. Okay, so did this work? Yeah, it gave us our 279. But the problem is that's not what we're looking for here. We're not trying to say, yeah, 97 and 79. We're on 8, that's 8. We're not trying to reverse the decimal digits. We're trying to reverse the binary digits, the bits, right? So could we get away with modifying this one? Well, actually, hold on a sec. Let me just put this in here. I mean, I'm only using this digit thing once, so I don't know if it's really that necessary to have a whole other thing for it. Let's just put these in parentheses so that it's clear where the parts are coming from. So a mod 10 is the other part over there. So let's run that, and is that gonna still work? Hopefully. Yeah, well, it's gonna still not work. It's gonna give us not what we're looking for in the problem here, but sort of an idea of what we're looking for this kind of thing. It's flipping the number still. Okay, so basically we don't want to flip the decimal number. We want to flip the binary number. Now notice we're using a 10 here, a 10 here, a 10 here. Oops. And that's because it's base 10 that we're looking for. But if we want to make it binary, would it be as simple as just turning the base into a 2? Well, let's find out. Let's run this. And it's probably not going to pass our custom test over here because, well, I mean, I gave it kind of a junk value anyway, but take a look. It's passing these ones. So, yeah, that's... I don't think this is really necessary anymore. That was just for testing the decimal version. But look, we're getting the 67 over here. We're getting the 1 over here. If we run the test, I think we should get all check marks now because we don't have that custom test throwing us off. Yeah, great. So sample test passed. Wow. Well, not bad. Okay, so this is kind of cool. We're able to use a process that worked for us in the case of decimal numbers. And we're basically able to just very easily migrate it over to binary numbers by just changing the base, changing the 10s into 2s. We could probably, if we want to do this in, let's say, hexadecimal, then we could just change the 2s into 16s or something like that, So we could do this for other bases. The point is these sort of number theory techniques are going to work for other base numbers as well. Okay, but I do want to take one last attempt at this because I want to make sure that we're keeping this in the spirit of bitwise operators. We're not exactly using a lot of bitwise operators here the way we're doing this. I think we can do better than that. So one of the things you might notice is that multiplying a number by 2, what happens when we do that? Okay, so like let's say we're dealing with 7. Okay, 7. Actually, you know what? Let's do this the long way. Yeah, that'll be fun. We'll do it the long way. Okay, so we've got our binary numbers. Our binary numbers, our place values are, well, 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, and that's probably enough for the example we're about to do. And let's say we've got a number which is going to be, what do we say? Hey, you know what? Let's go with 11. That'd be a classic example, right? 11. So let's go through it. Let's actually find out why 11 is the way it is in binary. I don't want to use any, memorization that we did before, but here, let's check it out. So does 16 fit into 11? No, it doesn't. So, there'd be 0 here. I'm not going to bother filling it in because we don't have any significant digits yet. Would 8 fit into 11? Actually, yeah, it would. So 11 minus 8 would give us 3. Okay, so 3 is what we have remaining. Does 4 fit into 3? No, it doesn't. Does 2 fit into 3? Sure, it does. And we'd have 1 left over. Does 1 fit into 1? Yeah, it does. Okay, so that's our 11. That's why it looks that way. Now, let's see. I think the way I want to do this is basically we'll multiply by 2. Okay, so 11 times 2 would be 22. So let's just choose a slightly different color for our 22. Does 16 fit into 22? Yeah, actually it does. So what's 22 minus 16? Oof, I'm not much of a math guy, but I think it's going to be 6. So does 8 fit into 6? Mm-mm. Does 4 fit into 6? You bet it does. And what would be left over? Well, 6 minus 4, we get 2. Does 2 fit into 2? Sure does. And we have nothing left, so 1 does not fit into nothing. Okay, so check it out. What we had here is basically we started with 11. That's what this one was. And then this one was 2 times 11, so this was 22. Notice anything about it? I mean, aside from the fact that 22 is 2 times 11, I don't think it's a coincidence that we arrive at this number by basically doubling each of the bits, right? So we can say that 11 is 8 plus 2 plus 1, right? So if we multiply 11 by 2, then we're multiplying the 8 by 2, the 2 by 2, and the 1 by 2, right? 11 is 8 plus 2 plus 1. So 2 times 11 is 2 times 8 plus 2 times 2 plus 2 times 1. Well, multiply the 8 by 2, we get 16. Multiply the 2 by 2, we get 4. Multiply the 1 by 2, we get 2. So basically, we're multiplying each of our bits here by 2. Hey, we're left shifting it. That's exactly what we're doing. This is a left shift. It's something we've seen before, right? We've left shifted it by 1. Every time you multiply a number by 2, you are left shifting it by 1. If you multiply it by 4, you're left shifting it by 2. If you multiply it by 8, you're left shifting it by 3. Okay, so basically, instead of saying b times 2, let's do a b left shifted by 1. Okay? Makes sense? And then maybe we could take a look at the reverse of this as well, right? We could sort of say, well, hey, if we wanted to divide by 2, so 22 divided by 2, we would right shift each of these bits by 1, right? But then what would happen? I'm just going to clear this, so hopefully everyone's... Actually, wait a sec here. Let's just do a big eraser on this so we can keep these here. Sorry if you still needed that. I guess you can rewind. Anyway, okay, where were we? So let me go back to kind of cool color. So let's say we had, well, let's start with 11 again. So I guess we don't need to repeat the calculation. I think it was this, right? Yeah, 8 plus 3, that's 11. Okay, great. So now let's say we want to right shift this by 1. All right, so we'd have a 1, a 0, and a 1. And then this 1 would just kind of get knocked off. It's gone. Well, take a look. 4 plus 1, we get 5. How is 5 related to 11? Well, it's kind of 11 divided by 2, but keep in mind, this 1 over here got chopped off. So basically, it's Math.floor of 11 divided by 2. So instead of saying Math.floor of a divided by 2, we could just right shift it by 1. Okay, so I want to start doing some of this stuff. So a right shifted by 1. And then this one would be b left shifted by 1. Let's try that. Hey, it's still working. Great. Okay, but there's one more thing. Because over here we're saying a mod 2. Well, what does that mean, a mod 2? It basically means we're taking a look at the end of the number and we want to know, well, is it a number like this, you know, like 11? Or is it a number more like, let's say, 6? That doesn't end in a 1, right? That's what we're saying, a mod 2, right? We're saying if we were to divide this number by 2, would we have a remainder of 1 or would we have a remainder of 0? So basically, okay, here's a good rule of thumb. And for anyone wondering, if we're looking at a binary number, we can sort of tell some meaningful information from this last bit here, or from the least significant bit. This is actually telling us if the number is even or odd. Okay, so if you have a 1 there, it's odd. If you have a 0 there, it's even. How do we know that? Well, if you think about it, you remember the place value for each of these things. We had like, this is the 1's place, this is the 2's place, this is the 4's place, this is the 8's place, etc., right? It goes on from there. But these are all powers of 2. There's only one power of 2 that isn't even. 2 is even, 4 is even, 8 is even. All these other numbers are even. So you add these on and you're always going to have an even number. The only way we can make it odd is to put the 1 in there, okay? So if you don't see a 1 here, if this is a 0, it must be even because it's the sum of just even numbers. If you see a 1 there, it must be odd because it's the sum of some even numbers plus a 1. That's going to make it odd. Okay, so basically one way of checking if a number is even or odd is doing that number mod 2. Another way of checking would be to just literally say, well, is this least significant bit a 1? So we could do, and this is one that we would have seen in the previous task, we could do a bitwise AND with just 1, or in other words, like 0, 0, 0, 1, right? So basically, if we AND these, we get 0. AND these, we get 0. AND these, we get 0. AND these, we get 1. But if we were to AND these ones, we get 0. So basically, it's giving us what we're looking for. We just want to do AND 1, okay? So instead of a mod 2, we're going to do a and 1. Keep in mind, that's a bitwise AND. It's not a Boolean AND. It's not a logical AND, so it's not double. It's single. It's bitwise. Okay, we are almost done here, folks. There's just one more thing. Here we're saying a is assigned the value of a right shifted by 1. This is kind of like saying, you know, a is a divided by 2. But we wouldn't normally write that. We wouldn't say a is assigned the value of a divided by 2. We would say a divided by equals 2 to be more efficient about it, right? So we could do the same sort of thing over here. We don't have to say a is assigned the value of a right shifted by 1. We can say a right shift equals 1. And that is pretty cool. Okay, so that, well, let's see if it passes the hidden tests. And yeah, it does. Okay, so I would actually say I like this one the best. I realize that some people might look at this one and say, well, yeah, but this one's one line, man. Come on, you gotta love that. And in some ways I do love that, but in some ways I don't love it so much. I mean, the thing I would say about this is basically, again, like I've said before, you know, this puts a new array in memory, puts a string in memory. We're not accepting this number for what it is, a number. We're trying to turn it into a string and then an array and reverse it and all that. Instead, we can just use bitwise operators, just go through the loop, go through the number one time, and we're done. We get it. ATD 285 asks, is the second argument in parseInt for specifying the base of what you're passing in? You're exactly right. Yeah, that's it. So normally, like you've seen before, right? We normally do parseInt without a second argument, which would just assume that it's 10. You know, like if I put this in here as a 10, it's the exact same as not having it at all, because that's just the default. But yeah, we're putting in the 2 just because we want a binary number here. So yeah, great question, man. Thanks for asking. So I think we're all done here, right? This passed and everything. It passed all the tests. So nice job. I mean, let me know if you have any questions, comments, or concerns. And I guess we'll wrap it up there. I don't think there's more to be said for this one.